we do reactions that are either exothermic or endothermic, we can use a stoichiometric process to determine how much heat is absorbed or released in the process. Some concepts of working with this is that if we reverse a reaction, the sign on the enthalpy changes. So this first reaction, turning copper 2 oxide and copper 1 oxide, is endothermic with a positive delta H. If we reverse reaction, take copper 1 oxide, turn it into copper 2 oxide, it's now exothermic with a negative delta H. The standard way of providing the enthalpy of a reaction is to give the enthalpy in terms of kilojoules, but it's just kilojoules, it's not kilojoules per mole. So how much is that for? Well, it's for the reaction as written. So in this particular reaction, that 288 kilojoules is per 4 moles of copper 2 oxide. If you do the division, that means it's 72 kilojoules per mole of copper 2 oxide. The 288 kilojoules is also for 2 moles of copper 1 oxide. If you do that division, you get that we have 144 kilojoules per mole of copper 1 oxide. The 288 kilojoules is also per 1 mole of oxygen. So the enthalpy of the reaction is written for the reaction as written. And third part is if we have to multiply our reaction. So we're going to be adding a couple reactions together using Hess's law. So if we multiply a reaction by a factor, we are multiplying the enthalpy of the reaction by the same factor. So in this case, if we divide the original reaction by 4, we want it to be on a per 1 mole of copper 2 oxide. So we divide it by 4, so we divide the 288 by 4 also to get 72. So Hess's law is that if we add up a series of reactions, reaction steps to get an overall reaction, if we add up the heat of those reaction steps, we'll get the heat of the overall reaction. So we can get heats of reactions that are hard to actually conduct in a lab if we can devise a series of steps for reactions that we can measure that add up to the overall reaction. So in this example here, if we want the enthalpy of the reaction for the decomposition of sodium bicarbonate into sodium carbonate, we look for the reactions that we can have. In this case, we're using formation reactions. So if we take the formation reaction of sodium bicarbonate, formation reaction is the reaction of forming that compound from the elements in the standard state. So we have tables of formation reactions and formation heats. So we look up the heat of formation. Sodium bicarbonate is minus 947.7 kilojoules. Well, we need 2 sodium bicarbonates for the overall reaction. And it has to be a reactant, not a product. So we switch this around and multiply by 2. That means we change the sign from negative to positive. We multiply the original value by 2 to get 1895 kilojoules. We can look up the heat of reaction for sodium carbonate. It's minus 1130.8 kilojoules. That gives us 1 sodium carbonate as a product, which is what we're looking for. Heat of formation of carbon dioxide, minus 393.7 kilojoules. And again, we have 1 carbon dioxide as a product, which is what we want. Heat of formation of water is minus 241.8 kilojoules. and it gives us one gaseous molecule of water as a product, which is what we want. When we do water, make sure that we're in the proper physical state. The heat of formation of liquid water is different from the heat of formation of gaseous water. So now we can add these 4 reactions up, and that will give us the reaction that we're looking for. So we're adding these 4 heats up, and that gives us the overall heat of reaction of a positive 129.1 kilojoules. So this is the endothermic reaction. Well, that example gives us the next rule, is that we can use heats of formation to calculate the heat of reaction of any reaction. So what it is, we're going to be using the heat of formation of all the products and reactions. We're going to add up the heat of formation of all the products times the coefficient in the balanced reaction that you're forming. So this Greek letter sigma means the sum of. That means we're adding up the coefficient times the heat of formation of each product. And then we're going to subtract all the sum of the coefficient times the heat of formation of all the reactants. So we're going to add all the products, heat of formation of products times their coefficients, and subtract all the heats of formation of reactants times their coefficients. And this works for all reactions. The heat of reaction will vary depending on pressure, concentration, physical state. So to simplify data presentation for ourselves, we generally are going to be giving data tables in terms of standard heats of reactions. So standard heat of reaction is based on 1 atmosphere of pressure for a gas. The international standard has changed to 1 bar. The U.S. has not caught up to that international standard, so we're still using the 1 atmosphere standard. For concentration, it's 1 molar concentration, and for pure substance, it's the most stable state at 1 atmosphere and 25 degrees Celsius, which is 298 Kelvin. So if we want to measure the heat of reaction, how do we do that? Well, we do that by using an instrument called a calorimeter, which is a heat isolating device. So it's to separate the heat of the system, what we're measuring, from the surroundings. We can do simple calorimeters of styrofoam cups to really fancy calorimeters that make heat exchange almost negligible. So if we're doing a reaction in a solution, there's a heat associated with the reaction, and that heat, if it's an exothermic reaction, that heat is absorbed by the solution. If it's a reaction, it gets the heat by absorbing heat from the solution. So the heat of the reaction and heat of the solution have an opposite sign. So if the reaction gives off heat, the solution absorbs it. If the reaction absorbs heat, the solution gives it off. So heat of solution and heat of reaction are different by change of sign. And normally we get the heat of reaction by getting the heat of solution through the specific heat of the solution. So if we know the specific heat of solution, or can make a reasonable guess, reasonable estimate of the specific heat of solution, such that if it's a dilute aqueous solution, we can use the specific heat of water. Then we can use the specific heat equation, measure the change in temperature, multiply by mass specific heat, and we'll get the heat of solution. We change the sign, and that is the heat of our reaction. Heat capacity. Specific heat is a particular type of heat capacity. We can do heat capacity in a couple different ways. So heat capacity is a measure of how fast something will change temperature as heat is added or removed. So we use the letter C to represent heat capacity. is going to be heat exchange in joules or calories divided by the change in temperature. And this could be for a whole object. So for a calorimeter, it's usually easiest to measure the heat capacity of the whole calorimeter, how fast the calorimeter will change temperature as heat is added or removed from it. Other times it's easier to reference the heat capacity based on how much material is present. There are two ways that we tend to do this. One on a per gram basis, per mass basis. The other one is on a per mole basis. On the mass basis, per gram basis, we call this a specific heat capacity. So specific heat capacity is heat is equal to specific heat times mass times change of temperature. If we want to calculate specific heat is equal to heat in joules or calories, the mass in grams divided by change in temperature in either Celsius or Kelvin. And with unit here, since the temperature is a change in temperature only, the units joules per Kelvin gram are equal to joules per Celsius gram, since the Kelvin and Celsius have the same degree size. If we have a large heat capacity means it absorbs heat well, so the temperature changes slowly. So a large heat capacity means a slow change in temperature. A small heat capacity means it does not absorb heat well, so there is a large change in temperature as we apply or remove heat. I think there was additional items on this list. I think I know where they went. But what's showing here primarily is the one that we want to know, liquid water. So this is the specific heat capacity that we want to memorize. Specific heat capacity is 1 calorie per gram degree Celsius. So calories based on the specific heat capacity of water. Well, since it's 4.184 joules per calorie, the specific heat of water is also 4.184 joules per gram degree Celsius. The other way that we tend to do heat capacity based on amount of substance is based on amount of moles of substance. This is called the molar heat capacity. So we use capital C sub m to represent molar heat capacity. So it'll have a similar form as specific heat capacity. It's Q, heat, equals Cm, molar heat capacity, times moles instead of mass, times moles times change in temperature. So heat equals molar heat capacity times moles times change in temperature. We have two common types of calorimeters. The most common is a constant pressure calorimeter. This is the easiest to work with, since we live in a constant pressure bath, 1 atmosphere of air. If we just have a beaker or styrofoam container that's not sealed, then it's at a constant 1 atmosphere of pressure. So a constant pressure calorimeter is the easy one to do. The heat of reaction at constant pressure, this is what we define as enthalpy. So heat at constant pressure is enthalpy, is delta H, enthalpy. And just as before, the heat of solution is negative the sign of heat reaction. So if the reaction gives off heat, the solution absorbs heat. And then our heat of solution, we can use specific heat to calculate that. Sm delta T will give us the heat of solution. So we need to measure the mass of the solution, the change in temperature of the solution, and that will give us our heat of solution, which will also give us our heat of reaction. And that will be heat of reaction at constant pressure, which means it will be our enthalpy of reaction. The other type of calorimeter is a constant volume calorimeter. So we have a sealed container where the pressure can vary inside. This is also called the bomb calorimeter because if it's not designed well or used well, it literally becomes a bomb and explodes. So in a constant volume calorimeter, there's no pressure. They cannot expand against anything, so there is no work. So internal energy is what's being measured. So we're measuring our heat at constant volume. Is this going to be a measure of our internal energy of the reaction? And again, the heat of reaction is negative of the solution, or calorimeter in this case. So heat of reaction is negative the heat of the calorimeter. Well, bomb calorimeters is usually easiest to measure the heat capacity of the whole calorimeter. So we take the heat capacity of the whole calorimeter with whatever constants it has, multiply by the change in temperature, and that gives us our heat absorbed by the calorimeter, the negative of the reaction. And for most reactions, our difference between our enthalpy and our internal energy are very small. So if we're not being extremely precise, we can estimate our enthalpy as being our internal energy. We got our list of equations, which means we're at the end of our chapter here. The couple relationships we need to know, or we don't need to know this last one. The charge of electron, we don't need to memorize the charge of electron.